everyone, thank you very much for being here. This is my first year in HealthFest, and it is a pleasure to present today one of my work, which is about newer approaches to data science in healthcare and personalized medicine. Before we start, just a quick disclosure that opinions expressed here are all mine and based on my research and contributions, and nothing of my own employer. Rumi captured it very beautifully. So your uncertainty comes from your longing for certainty. Fall in love with uncertainty and certainty will come to you. And basically that is the gist of my today's talk. We want to turn uncertainty into insight. Just a quick overview. First, why Bayesian? What are the applications of Bayesians? And where we can use them, and also how to model uncertainty, and one use case that I'm going to talk about today. So Bayesian models in general, they can help us quantify uncertainty, and that is very useful in healthcare, because in healthcare we have most of the time we have imperfect data, or any other industry. Most of the time data is not perfect. Either we have noisy labels, or we have limited data, data is scarce, and it is going to help in those cases. And today we will go through how they can help. And the way Bayesian model works is that, unlike a frequentist approach that all of us are familiar with, instead of coming up with some point estimates, they give us distribution of possibilities. So imagine something as simple as linear regression. In linear regression, we know that after solving for the parameters of the equation, we come up with 1 point estimate for a slope and 1 point estimate for intercept. And we come up, after we use Bayesians, we come up with distribution for the slope, all possible probabilities, and also the intercept. And we do that through Bayesian formula, which is shown here, and also priors, our prior belief, what we think about the whereabouts of the parameters. Also, using our evidence, which is coming from our data, we come up with a conclusion, which is our posterior, which is that distribution that we talked about. And so what are the key features of Bayesian models that make them so special and ideal for many cases? So the first feature is that we can incorporate our prior belief, and that can be very helpful when data is scarce and we have expert opinion, which can be the case in many medical cases. And the other great feature is that they can quantify the uncertainty and basically separate the uncertainty that we have, and it is coming from the data itself. The data itself is ambiguous. Imagine some radiology images, right? Or the model, the limitation of the model. We can clearly see the separation of those and quantify them. And actually, in today's case study, I'm going to show how it can help us come up with some better models which are more transparent and trustworthy. One of my observations by going through the literature and also being in industry and working with production models that use in production is that we are using Bayesian concepts in many state-of-the-art models nowadays that we have in AI, like computer vision models or large language models that everybody is talking about nowadays. We use those concepts, but we don't use them as much in the last layer of data science, which is production. And when it comes to decision making in finance, in policies, in medical application, we don't use them that much. However, nowadays, little by little, they are coming to the surface. For example, many companies nowadays, they use it for A/B testing. Instead of previously they used like frequentist approaches, nowadays they are switching to Bayesian models. Or at Genentech, for example, in commercial data science team, we use it for measurement and market mix modeling, where data is scarce, but we have expert opinions. That was my observation. Now let us go to the case study. I just want to give you a background that this study is the collaboration between University of San Francisco, and Oculus company. It is basically a peer-reviewed journal paper, and it is about classification of Meibomian gland dysfunction using these Bayesian models. What are Meibomian glands? Glands that are providing lipid for the tears. Basically, they prevent dry eye, and they are located on the top and lower eyelid, and their dysfunctions lead to discomfort and dry eye. And the thing is that it is totally preventable. I mean, not totally, but at least it is actionable. And if detected early, we can have improved outcome. And you can see the different stages of MGD here. The first one is when they are totally healthy and intact. But second image, which is grade 1, is when some of them are affected, but it is the onset of it. And the second and third are more advanced. And basically the last one is when we see chronic dry eye disease. So the objective of this study is that we wanted to come up with a fully automated MGD classification for cartograph device for Oculus. And we had around 4,000 images, 3,000 coming from this device, 1,000 from a public data set, and we wanted to come up with device agnostic model which is more robust than human. And what I mean by more robust is that this is one of the cases that we have a very low level of agreement, inter and intra, meaning that between experts and even for one expert, we don't see consistent classification for one image. And as you can see here on the x-axis, we have a stack basically 600 image, and you see that we show 3 different experts' opinion. They all have different classification for each image. And the higher level is showing the average. So in machine learning models, at least the one that we use, we only can work with one label. So eventually for each image, we had 3 to 6 labeling. We had to average them and consider that label as the label of that image. So what we did was that first we got an image, as you can see, the first image on the left. And we used the public data set that was provided for free publicly. And they had the mask for eyelid and MG. So we used those to come up with segmentation model so that we could segment eyelid and MG, and we could come up with the image that you see right. And we use those images and feed them, all of them, to the model. And this way it enables our model to learn more efficient and faster. We had around 4,000 images. We used 3,000 of those for training, and we kept 1,000 for validation. So we built a model. We used a base model or efficient net and also ResNet. Basically, these base models, they extract features from images, and we put some custom layer on top of it to do the fine-tuning. So what happened was that we used different architectures, but we couldn't exceed 60% performance in the validation data set, which is not great, as you know. And also what we saw was that model was quickly overfitting, meaning that they memorize basically the labels, and they cannot work very well on the unseen data, which is the validation. And this is not what we want for AI models. We want them to work well on unseen data. Our observation showed that the reason that it's not working well is that labels are very noisy. At that time, we decided to switch to Bayesian neural networks, which are very well working with noisy labels. And Bayesian neural networks are very similar to regular neural networks. The only difference is that their weights and biases are in forms of distributions. They are not numbers. And that is what enabled them to give us uncertainty in different formats and quantify it for us. So what we did was that we added 2 probabilistic layers. We used TensorFlow probability. We added those layers, and we managed to quantify uncertainty. And now you will see what I'm talking about from the beginning, how we can basically quantify those uncertainties. So as you see, it is one of the images that we have, right? The overlay of MG on top of the eyelid, and also You see on the x-axis different classes that we have, class 0 to 3. And also those lines stack on top of each other, basically. They are the predictions of the model, the distribution. So as you can see, and the green means that it is the actual class of the image. So basically this is a very advanced case, and it is of grade 3. And model also is predicting it correctly. See, in deterministic models, whenever you run a prediction for an image, every time you get one answer, and that answer never changes. Like if it is saying it is of class 2, next time you run it, it is again the same thing. But in probabilistic models, it's not the case. Every time you run, it gives you one set of probabilities, right? And so what we need to do for probabilistic model is that we run multiple prediction. We called it forward path. We ran 100 forward paths for each image. And we basically plot this image that you see here. That is showing us what number it showed us every time. For example, maybe one time it is saying that the probability of class 2 is 20%, class 3 is 80%. Next time it is telling us the probability is 25, the other probability is 87. And together they should add up to 1. And as you can see for this case, for example, consistently every time we get that the probability of class 3 is higher than 2. So basically model is sure about that. There's no question, right? However, we saw two patterns in the data. In some of them, model was very sure there was a huge gap between two different classes. In the other one, you see they have overlap. When they have overlap, it means that sometimes models say it is class 3, sometimes say it is class 2, like a human being, right? And it is coming from the ambiguity of the image itself. And the fact that it is actually not black and white, it is something in between. Maybe it is 2.5, right? At least here we could see if model has learned anything. Before we had no idea. It was like a random prediction. Sometimes it was right, most of the time it was wrong because you saw performance was not great. But one thing that happened was that even this time performance was not great either. Performance was around 61%, but we could see that model has learned the pattern. But one thing that we saw was that many times when the model prediction is not correct, it is either because the image is ambiguous, right? So sometimes it is predicting correct, sometimes wrong, because it was oscillating between two possibilities. Many times it was wrong, and when I am not an expert in MGD classification, but I could see that by looking at thousands of these images, that actually maybe model is more right than the average score. And at that time it occurred to my mind that okay, let us refine labels. And the interesting thing was that when I was looking at the wrong prediction of the model, which was making more sense, when I was checking the labels given by annotators, it was actually in the list, but the average was different from that. And the reason is that, as you know, average is affected by outliers. So what we did was that we used the model to refine those labelings. Algorithm works is that the ones that the predictions was wrong, but the model was certain that prediction should be this. We were checking if that wrong prediction is in the list of annotators. And that is very important point. We didn't let AI dictate what should be the class, because we all know that AI can have errors, right? If it was in the list, we were changing the label. If that case was not passing all of these three conditions, we were keeping the label as it was. And that way we came up with new labels, and we changed almost 14 to 15% of labels. After changing the labels, we trained another model using the same architecture. We used EfficientNet. EfficientNet was working better. So see, at the beginning, the performance was 61%. Then we changed almost 14% of labels. So naturally, without doing anything, performance jumped to 75%. But then we trained the model with the new labels, and the performance improved drastically. I mean, 11% is a lot in any AI model. Actually, visually, we could see that improvement. So it jumped to 86. Actually, it could get most of them correct. The ones that it was not getting correct, mostly because of a specular reflection, model could not segment the eyelid or MG correctly. And those were the wrong predictions. But mostly, it was very clear that the model learned the pattern. And we also tried it, maybe it is just architecture specific, just to make sure it is not architecture specific. We also tried ResNet, and also with ResNet we saw a huge improvement. Basically, we can use Bayesian models to come up with some more trustworthy and also interpretable models, and the models that are actually acting like a human being, like saying, oh, class A is possible, and also maybe class B, something like that for clinicians.